So let us take a specific example where this is applied. So let us take the case of concentric spheres, okay, and let us assume that this is a solid sphere in between and there is a vacuum space, and this is, let us say, maintained at some temperature T1 and this is maintained at some temperature T2, and the inside curved surface area is A1 and A2. Outside curved surface area of first object is A1 and the inside surface area is A2. Okay. How many view factors are there? So what are all the possible view factors? F11, F12, F21 and F22. These are the four possible view factors. F11 is 0. So the non-zero view factors are 3, but there are actually 4 view factors. One is 0, it is trivial, but these are 3 non-zero view factors. Okay, how do we find them? How do we find the other 3 view factors now? Yeah? So I claim that you can do it without integration. Yes. F12 will be 1, okay. Correct, correct. Okay. And use the summation rule, the same thing. So we know from summation rule F11 plus F12 is 1, right? But we know that F11 is 0, it is a convex surface. So F11 is 0 because it is a convex surface. It is a convex surface, and from here F12 equal to 1. F12 equal to 1, in fact one could easily intuit, right? Because it is a convex surface, you expect that no radiation emitted by the surface 1 is going to be received by itself, which means that all the radiation that is emitted has to be received by the second object if it is a closed system. So therefore F12 should be 1, which means all the radiation emitted by surface 1 is actually intercepted by surface 2. Alright, so now we have reciprocity relationship. Which says that A1 F12 equal to A2 F21, right. So it essentially relates the view factor from surface 1 to 2 and from surface 2 to 1, okay. So from here we can find that F21 will be equal to A1 by A2, okay. So that tells you what is F21. So that is the view factor of emission that is radiated from surface 2 and as intercepted by surface 1. Okay. What about F22? So F22 is nothing but 1 minus F21 simply by summation rule. Okay. By summation rule, F22 is 1 minus F21, okay. So now we can write the view factor matrix, okay. So F11 is 0, F12 is 1, F21 is A1 by A2 and F22 is 1 minus A1 by A2, okay. So note that we did not do any integration. So depending upon the system, you may have to integrate, you may not have to integrate. So I will show you some other example in a short while where there is no other way other than to integrate the expression to get the view factors. So you first have to intuit as to what is the geometry and can we find out the view factors without doing the gory integration. So the question is, if I take differential element, how to make this argument, right? So if you take a differential element, okay, supposing I take a differential element here, okay, So it's emitting radiation in all directions and equally if it is a diffuse emitter, and so some of it is received by here and some of it is received by some other place. So now one could actually, you should construct a three-dimensional angles, and if you do the integration, this is exactly what you will find. Yeah, it doesn't matter, no. F12, whatever emission that goes out from here, right, they are all always going to be received by 2, irrespective of whether it is a point source or a differential element, because it's a convex surface. Due to the nature of the geometry, whatever emission that is going to come from this surface is also always going to be intercepted by surface 2. And the question is, what if there is only one small location where the emission is occurring, not from every section in the surface, correct? Is that the question? Yes. So now you will have to account for what is the surface of that location, and in fact may not be today's lecture. Next lecture we probably, I'm going to show you an example of how to find out the view factor if you have a differential element on a sphere. So when you say non-uniform, you really mean that not all locations on the surface is emitting radiation, right? So we're going to see that in the future. Any other question? Okay. It could be. So for example, you could paint with different colors and you could change the emissivity. So note that emissivity is a surface property. So you change the properties of some locations of the surface, you're going to change the radiation properties. Alright, so next we are going to look at divided surfaces. Okay, we're going to look at divided surfaces. So let's say that there is a surface I, and there is another surface, okay, and in principle without loss of generality we could assume that different parts of the surface are actually having different properties. Whatever way by which you achieve them, and so you want to now calculate the view factors for individual exchange between these fraction of the surface. So overall surface is, let's say, called J, and so you want to know what is the view factor for radiation exchange between surface I and the individual surface. So there can be two situations. Situation 1 is where each of these surfaces will have different properties, or it could be a complicated geometry. So instead of estimating the view factor for the whole surface in one go, you may want to divide them into small pieces and find individual view factors and find the overall view factor for surface J. Okay, so there could be two reasons for doing this. Okay, all right. So now, by definition, the overall surface of surface J is nothing but sum over all k going from 1 to n. That's obvious. Okay. Now, AI Fik, okay. So I want to calculate the view factor between I and any other surface k, okay, and that's also equal to AK Fki by reciprocity relationship, right. So now I want to find AI Fij, okay, right. So that's nothing but Aj Fji, okay, that's from reciprocity relationship for the overall surface, okay. So that should be equal to sum of AK Fki k going from 1 to n, right. So it's just a sum over all the divided surfaces, right. Any questions on this so far? Okay. So now Fji is nothing but sum k equal to 1 to n ak into fki divided by aj. Okay. What is aj? That is nothing but sum of all the individual areas, right. So, that will be fki 1 to n divided by sum over all areas. Okay. So, what this expression tells you is that fji, which is the overall view factor between surface j and I, is simply given by sum over the fractional area multiplied by the corresponding view factor. What is ak by sum aj? It is the fractional surface area, right. So, if I call small f as the fractional surface area, ak by sum, that is nothing but ak by aj. So, fji is nothing but sum over all k fki. Okay. So, that is an important relationship. So, if we have divided surface, then you could use such summation formula to find the overall view factor between the two surfaces. Or if you know some of them, you should be able to calculate the view factor for the other divided surface, for which you may want to calculate some of the radiation properties. So, we are going to look at a specific example now, where we do not have a choice but to use the integrals. Okay. So, let us say you look at the coaxial disk. Okay. So, this is surface j and this is surface I. Okay. And if the surface area is ai and if the surface area is aj. Okay. So, as a first example, I will assume that ai is much smaller than aj. So, we assume that ai is a point source. We will relax this assumption in the next lecture, where I will show that there is another method to calculate when ai is not a point source. Okay. So, right now assume that ai is a point source. So, let us construct a geometry. So, supposing I take a differential element. Okay. Okay, I take a differential element and let us say that the centers are connected, I mean it is not connected, it is aligned. Okay. And if this separation distance is, let us say, L, and the diameter of the larger disk is d. Okay. So, let us say that, so note that when we define the view factors, r is the distance between the element that you are considering and the emitting element, right. So, if this distance is r, okay, and I refer this as small r, and if I say that the thickness is dr, dr is the thickness of the element. Okay. So, note that it is a 3-dimensional system now, you actually have a cone, right. So, it is a element which is actually a ring on this surface, and so the solid angle is essentially because of the cone which is subtended by this element on this surface. Okay. So, the view factor Fij is given by 1 by ai integral ai aj cos theta I theta j divided by pi r square dai daj. Okay. So, I have assumed that I is a point source, so I can simply integrate it out, and so this is essentially integral aj cos theta I cos theta j divided by pi r square into dAj. What can we say about theta I and theta j? What is theta I? Theta I is this angle, this is theta I and this is theta j. By simple geometry we know that they are one and same, and so this will be integral Aj cos square theta j divided by pi r square into dAj. Okay. What is cos theta j? Cos theta j, look at the geometry, it's L by R, so it is L by square root of L square plus R square, right. So R is this distance here, so the hypotenuse is square root of L square plus R square, so cos theta j is L by square root of L square plus R square. And R is square root of L square plus R square. What is dAj? dAj, what is dAj? 2 pi r dr, 2 pi r dr. So we plug in all these in the integral. Okay. So it will be Fij will be integral 0 to d by 2. So that is the radius from 0 to d by 2, and cos theta square is L square by R square plus L square into 1 by pi. R is root L square plus R square, so it will be 1 by L square plus R square. So we have 1 by R square, and dA1 is 2 pi r dr. Okay. So we can integrate this. So pi goes away, and so it will be L square d by 2 2r dr divided by L square plus R square the whole square. Okay. How do we integrate this? You make a substitution, right? So you say u is L square plus R square and du is 2r dr. So you plug in all this. So the view factor Fij will be d square by 4L square plus d square. Okay. So the view factor is d square by 4L square plus d square, where d is the diameter of the larger coaxial disk and L is the separation between them. Okay, is that clear to everyone? Okay. So in this particular case, we have no option but to do the full integration. You have to, one important thing you have to keep in mind is whenever you do this integration, these area that you are calculating and the solid angle, it involves 3 dimensions. So you have to be very careful how you construct the geometry. So this is a very simple example where constructing the geometry is very easy, but there are many cases where constructing the geometry can be completely non-trivial. So I really encourage you to take different examples from your textbook. In fact, there are tables in your book which tells you what is the view factor for different shape geometries, and you should really attempt to derive these view factors and convince yourself that you are able to construct the geometries properly. So all the expressions given in the book are right, so you should be able to convince yourself that you are able to derive it. It is very important to learn how to construct the 3-dimensional angles and 3-dimensional geometries.